experiments. For example, if I don't have an atom and I have some initial state for my field, whatever happens, the photon will fly very, very quickly at the speed of light. It will hit the environment, it will get absorbed, and it will be disappeared. That means the system, the free radiation field, has a so-called environmentally preferred state, or a pointer state. This term was introduced by Zurek, and it's the state, the natural state of the system. That's kind of the preferred state. You could say maybe the preferred state would be a thermal state, but in the optical regime you would go to very low temperatures to find something else. Then essentially you always end up with the vacuum state. Yeah. So these photons are absorbed, and your atom is always sitting in an environment where the field is essentially the vacuum state. If you have an atomic system, then the atom interacts with the field, but then the effect of the environment can still be modeled in this way by saying, after a very short time, the field will be in a vacuum state, and the only way, if the photon is absorbed further away from the atom, the only way how this can happen is that the state of the atom changes in a way that you take the trace over the field, because otherwise all the statistical properties, like how likely it is to find an atom in one state or another, would change within the absorption process. But the absorption of a photon happens some distance away, so it shouldn't change the statistical properties of the atom. Or it's not a process, for example, that can change the energy of the atom. And these are the kind of assumptions that we use to derive master equations. So initially what we have is, for example, an atomic density matrix. And because photons get absorbed anyway, we can always assume that our initial state is one where the field is in the vacuum state. And if I then look at the time evolution of this initial state, then what you have is, so here's our initial state. What I have is I have an interaction of the atom with the free radiation field. So if an atom is excited, it will transfer its excitation into the photon field, and then these photons will fly away, and once they get absorbed, I trace out the field, and then that will tell me how the density matrix of the atom changes from one initial time t to a short time later, t plus delta t. And then once you know how this density matrix of the atom changes, you can rewrite it as a differential equation. You can say this density matrix minus the initial density matrix divided by delta t, so I can calculate the derivative of the density matrix. And then you would get an equation of this form, which is the quantum optical master equation. The first term, as we will see later, describes the dynamics of an atom whenever no photon is found, and it shows how the state of the atom changes when no photon is detected. And if you detect a photon, then you know that your atom has gone into the ground state, and that's reflected by this term. So this is kind of the mathematical formalism that we use. So in order to describe quantum optics experiments, we often use master equations. But because when we use density matrix, then this would be the equation that describes how an ensemble of many system changes. But then you can also, by distinguishing whether you measure photons or not, that will show you, so you can unravel this master equation into individual trajectories. And if you detect a photon, you know an atom would be in the ground state. But it also evolves in time if you don't have a photon emission, if you don't see a photon emission, and then this dynamics would be described by a Schrödinger equation, where you have some non-Hermitian conditional Hamiltonian. So what I want to show next is, I want to show you two experiments that has helped us to develop this kind of quantum optics formalism, because, so you could ask, well, how do we know that this is actually a good model for for describing the interaction between a single atom and the radiation field. And one of the experiments is an experiment that was proposed in 1975 by Beige. So at the time, people had come up with ideas on how to trap a single ion similar to what I described before. So you can isolate a single ion in free space. It's sitting there, and then you can apply laser driving, and you can look at the photons that are coming out. And what Beige predicted was that if you have a ground state and an excited state that decays very quickly and emits photons very quickly, and you drive it strongly, then what you expect is a constant stream of photons coming out of the system. And then his idea was to simultaneously couple the ground state to a very long-living state. And what you might expect is, if this is very weak driving compared to this driving, you might expect that this weak driving has almost no effect on the light emission from a single atom. But this is not what happened. What happened was something, what he predicted was quite different. And what he predicted was a random fluorescence signal. So this is a picture from an actual experiment. So what happens is that the atom gets excited, it emits photons, but sometimes there is a chance that we do not see a photon for a while, because there's always a small amount of population here, so there's a very small probability of not seeing a photon. But once you don't see a photon coming out of the atom, you kind of learn that it has to be in this state. And once it is in this state, it no longer sees the laser driving and will stay there for a very long time. But because when the atom is in this state, there's also a small population in the ground state. So there's always a small chance that the atom gets excited and emits another photon. And when that happens, then it would return from one of these dark periods into a light period. So this is, and having these very random telegraph fluorescence signal, which was called macroscopic quantum jumps, tells us that this kind of picture that an atom is something that sits in a free radiation field, it generates photons, and these are then measured by the environment on some kind of coarse-grained time scale, is a very good picture of describing this kind of experiment. So once we know what is happening, or let me describe more how we model it. So this is a bit repeating what I said earlier, but maybe it makes more sense now. So what we have is we have a Hamiltonian that describes an interaction between the atom and the radiation field. That would be an exchange Hamiltonian that takes excitation from the atom and puts it in the radiation field. But then you also have, because you have a single system and you have an environment that observes the system, you also have detectors surrounding the ion that would tell you if a photon has been emitted in a certain direction. And then you can calculate, if you detect a photon in a certain direction, how does the state of the atom changes? And that's normally described by a reset operator, which is essentially the operator that lowers the excitation in the atom. Yeah? So if you detect a photon, then that energy is no longer in the atom, and the atom has gone into the ground state. And just by assuming that the environment measures, you can calculate the right probabilities for an atom to emit a photon, and you can reproduce this behavior. What puzzled people a little bit more is that the state of the atom also changes when you don't see a photon emission. So if you have an atom that is, for example, in a superposition of ground and excited state, and you don't see a photon emission, so the environment does not absorb a photon for a short time delta t, what that means is you learn something about the state of the atom. So that means after a time delta t, we have to update the state of the atom. So you get some kind of non-unitary dynamics. And the longer you see no photon coming out of an atom, you know that the atom wasn't excited in the first place. And that also creates, so you slowly, any excitation that was initially in the in the excited state, under the condition of not seeing a photon, it gets dammed away, and the atom also goes to the ground state. So in this way, for example, if you have an atom that is half excited, half in the ground state, the probability of not seeing a photon would be 1/2. When you see a photon coming out, you see a whole photon, and your detector will make a click and absorb the energy h bar omega from the atomic transition. But if you don't see a photon with probability 1/2, the atom will also be damped down to the ground state, and this is what this non-Hermitian Hamiltonian describes. Yeah, so you have some kind of nonlinear dynamics and a damping into the ground state under the condition of no photon emission. And that's what we know. So even if we only half excite a single atom, after a short time it will be in the ground state, and it will either have emitted a photon or not have emitted a photon. So when you have this formalism, you can simulate single trajectories, and that's an example of a numerical simulation of the kind of trajectories that I was showing here. So this is an experimental picture, and really the only difference between theory simulations and the experimental pictures is that in the experiment, when you have a dark period, your fluorescence rate doesn't go down to 0 because you always have a bit of background noise. But otherwise, the signals that you can generate on a computer using this quantum jump approach, this quantum jump simulations, looks exactly the same as what you would get in an experiment. Yeah. So here, this shows the population in the state that cannot emit a photon. So whenever you see photon emissions, and if you see photon emissions often, then you kind of learn that the atom is not in this state. It is somewhere between these two. But there's always a small probability of finding the atom in the state that cannot emit. So if you don't see a photon for a short time, that might mean your atom is in the excited state. And then the longer you don't see a photon, the more the population in this state is increasing. Yeah, because the more and more likely you gain more and more knowledge that atom must be in the excited state. So it does exactly that. It goes into the excited state. So into the state that I was showing here that cannot emit photons. So you have this nonlinear transition into the dark state, and then it will stay there for a long time. And then, but while it is in this state that it cannot emit, there's always a small probability that it returns to the ground state and generates photons again, and eventually that will lead to a transition. But what we have is that these light and dark periods that are showed here, they're completely random, and they are also very, very long. Initially, this caused some discussion because when quantum mechanics was initially developed, it was developed to describe ensembles of systems. So you always calculate probabilities, expectation values, ensemble averages. And Schrödinger initially said that maybe you shouldn't apply quantum physics to single systems. That would give nonsense, like the quantum jumps that I just showed. And Bohr back then, they were arguing that maybe that's just a matter of doing these type of experiments, and they have become possible. So the ideas on how to trap single atoms goes back to the 1970s, and then in the 1980s, the first ion traps experiments were realized. These experiments really contributed a lot to how we understand quantum physics now, and how we describe it. So a lot of people in the 1990s, 1980s found those experiments very puzzling, but they really put the foundations on how we model the interactions between single atoms, lasers, and how we describe photon emissions. So let's have a look at another experiment, which was performed a bit later, but it's also puzzling when you think about it. And that was an experiment that goes back to Scully and Drill Scully proposed to do this experiment in 1982, so quite a, even before people started doing these kind of experiments. And what he suggested is to trap two ions next to each other. And then a laser excites these two ions and they emit single photons. So, and then these photons drive away. If you think of an atom as something that emits single photons, then you might expect that the photons will just fly to a faraway screen, and you would see just like if you have only one atom there, or one ion, you just have photon emission onto the screen, and you will see some, yeah, you will just clicks equally at any angle. But what happens when you drive two atoms? The laser should be coming from the side. They came from the side, so the laser light is not going to the screen. When you have two atoms, then and they are relatively close together, then what we don't know is which atom was actually creating a photon. And what Scully and Thrissur predicted was that what we will see on the screen is actually an interference pattern of the light that is coming from both atoms. And that is puzzling, because if you think of an atom, of atoms as something that emits spontaneously photons, then we wouldn't expect the interference. But like I said, because these atoms, they don't emit light individually, but they emit light both together collectively. That's why we get an interference pattern on the screen. So in order to model this theoretically, we can proceed exactly as we did before. We assume that the atom sits somewhere. We have two atoms sitting in the free radiation field. Both atoms couple to the same radiation field. That means both atoms generate excitation in the radiation field, and it's only when the light arrives at the click that at the screen, then a measurement is performed whether there is a photon or not. And so up to there, you have to think of the light that's coming from the atoms really as waves, and those waves from the two atoms interfere. So, for example, now you can, proceeding as before, you can calculate what is the state, how does the state of the atom changes when I detect a photon that's come from a certain direction, so at a certain point of the screen, and you will always see that there will always be contributions from both atoms. And depending on the state of the atom and where the light is detected, you will have sometimes constructive and sometimes destructive interference. And this is illustrating that again. So because we have the effect that creates a photon at a certain point is a contribution from one atom and the other. If you multiply these out, you get the terms that you would have if you had only this atom or only that atom. But you also get terms when you have like a 2 here and a 1 on this side. So you get the interference. And this is really the interference, if you want, of spontaneously emitted photons. So a lot of people were saying, don't talk about spontaneously emitted photons. Some people in the quantum optics community didn't like the word photon at all when it came to describing atoms. So it's better to think of the atoms as like dipole antenna that send out light and waves that then cause clicks at the screen. And the photon really only is created on the screen in the detection process. And but these interference effects, they are interesting because they can create interactions between the atoms. Yeah? So when the atoms are very close together, they really emit as if there's only one dipole. So this is the signal that you would see, what you would see on the screen if you had like only one atom or two atoms very close together. But when you move the atoms a bit away from each other, then an interference pattern forms, which is exactly as it would be in a classical interference experiment. But it's slightly more because where the minima and the maxima are depends on what states your laser is preparing. So changing the phase of the laser would shift the interference pattern left and right. And this is a picture from the actual experiment. So when this experiment was performed in '93 with 2 ions, and they collected the photons. So these are the photons that are collected from the 2 ions on the photographic plate, and you clearly see these interference patterns. And for example, when they could tell, when they would do a measurement on the ions to see which atom was emitting the photon, then they can make this interference pattern disappear. So if you keep the information, which atom emitted or which ion, then this interference effects disappear. Okay, so now you might be asking yourself, why am I talking about experiments that have been performed 20 years ago or almost 30 years ago now? But the physics that's underlying these kind of systems, or these 2 experiments that demonstrate how we should model quantum physics when you talk about atom field interaction at the level of single atoms and single quantum systems. These are exactly this is the physics that people are now exploiting when they develop new quantum technology. So what I will do for the next few minutes is I will give you a very rough, quick introduction to quantum technology and quantum computing, and then we will see how the experiments the effects of macroscopic quantum jumps and double slit interference, how that can be used to implement tasks in quantum computing. So if we go a few decades back, and we don't have to go back very far, then technology looked very different from what it looks like today. Cars have changed. Maybe cars haven't changed that much. They don't look as cool anymore, but computers definitely have changed a lot in the last 50, 60 years. Since, so that's probably something from the early 1980s. So recently there has been a huge leap in quantum in technology in general, mainly by it comes from miniaturizing the components of computers. So cars haven't changed so much because you still need an engine to drive, but the kind of features you have, it tells you how you get from A to B. It helps with navigation. So there is a lot of changes, and also computers have become much more connected. It's not always making our life nicer. I find these pictures quite horrible, but it is definitely a change that is happening. Cities look different now than they used to look like in just 50 years ago. And this kind of change in technology is happening more and more rapidly. And a lot of people expect that what will happen to the next change in how we process information, for example, will come from quantum technology. But quantum technology has also a lot of other applications. Here are these pictures are a bit out of date already. Initially, quantum technology, people thought about applications would be quantum communication. So if you use entangled photons. So there are already many quantum crypto companies that are selling cryptographic devices. Probably the oldest quantum technology is quantum clocks. So if you have a radio-controlled watch, the signal has been calibrated by a single ion somewhere in a National Institute for Technology. There is a single ion that emits macroscopic quantum jumps, and this effect is used to calibrate atomic clocks, who then send you a signal to calibrate your own clock. There are different quantum components. So quantum imaging, especially for medical application, I think is an application that hopefully will help, especially now in times of COVID. Hopefully there will be, if it will become much easier to detect viruses, it will help a lot, but also detecting things like glucose for people with diabetes, making all these things easier, would have a big effect on our lives. And then quantum computers are seen as something that is much more was seen as something that's more in the future, and also communication of having whole quantum networks. But if you look at the news, a lot of these kind of applications are becoming available right now. So one way of, okay, so the idea that I should explain more why we think that quantum computers will make a difference. The idea of quantum computing goes back to Feynman, for example, who did a lot of calculations of modeling quantum system, which is a computational hard task. So even if you have a computer, if you want a model describe a system that has more than, let's say, 50 atoms, it becomes very hard to do it on a computer by using all the microscopic interactions with there, and we need a lot of approximations and techniques to still get good predictions for experiments. So he realized if you had a computer that would behave exactly like the problem that you want to solve, like the quantum system itself, it would be much easier to make predictions of what is the physics of these quantum systems. So there would be a lot of advantages there. And there are also other hard computational problems that are very similar in difficulty to solving modeling a quantum system. So that quantum computers will also have other applications. The basic idea of a quantum computer is that instead of storing information in 0 and 1, you would store it in a qubit, like an atom in one ground state, or an atom in another ground state. Yeah, so ground states of atoms are degenerate, so you could have one ground state where your spin is up, or another ground state which corresponds to spin being down. And then you would encode information in there, and that means you can store a lot more information simultaneously. So instead of preparing your register in 001, you can prepare it in all possible states 000 up to 111 simultaneously. Yeah, so you don't know which information is in there, but you can kind of prepare these superpositions, and you can prepare non-entangled states and entangled states. And then in order to process the information in the register, classically you would do NAND gates that changes the state depending on, I forgot what this gate is doing, but it gives you a 0 only when you have a 1 and a 1. On the quantum level, you process information in the same way by applying unitary operations. And then this can be used to do quantum simulations. For example, people have shown that when you have a quantum computer, you can solve any problem that also a classical computer can solve. But for example, adding numbers would become a task that is difficult, while things like factoring a number, which is hard for a classical computer, and it's a computational hard problem, would become easy. But if you have quantum and classical computers working alongside, then you would their capabilities would be a lot more than what we have now. So we would make computers a lot more clever than what they are now. And this is an example just to show how what the idea is. So in a classical computer, you can only have numbers like 001, while in a quantum computer you can have these superpositions of states. And what that essentially means is that when you have a computation, let's say you start here and you want to go there, instead of only being allowed to process your information by going along this grid, along numbers, you can now take your computation can move your register on a more direct line from here to here. And you see, even in 2 dimensions, that immediately saves you a factor square root of 2. Yeah. So if you take a taxi in New York, and you have to drive along the roads, and getting from A to B will always be longer than if you take the subway, where you can travel in a straight line. Yeah. So in the quantum computer, by being allowed to have superposition, you can design algorithms that can take you from your input to your output in a more straightforward line. It's not really an explanation how quantum computers work, but I think hopefully it illustrates that there is a huge enhancement that you can have. And in a computer, you're not working with 2 bits only, you're working with highly dimensional systems. So these shortcuts and what you can save is quite enormous if you can. Yeah? The computational time you can save by going more directly from your input to your output, it can be exponentially fast. So how we implement quantum computers, or how people implement it, is initially people played with linear optics experiments. So they had single photon sources and sent them through linear optics setups, and an experiment would be performed on an optical table that looked quite messy. Now a lot of these systems have been miniaturized, but the physics behind is still exactly the same. So instead of having an optical table with beam splitters and phase shifters, things are written on a photonic chip. And this is a picture that I found in the internet that's from PsiQuantum. PsiQuantum is a company in America that had set out to really realize quantum computing with thousands of photons, and they're writing photonic structures on silicon chips. So they have single photons integrated onto the chips. They create large arrays of highly entangled states, and then do measurements on those states in order to perform a computation. And there is huge progress happening. So these companies have lots of money. Other people have companies, or they're trying to implement quantum computers with the kind of ion traps that I was talking about before. So they shine laser light on single ions, do measurements, and control their states. Again, initially ion trap experiments looked like this in the 1990s or early 2000s. Now people have miniaturized. Ion traps are the structures are written also on chips, and then ions are floating above those chips, and they can be moved about. So there's a lot of progress in technology. So the difference between these kind of experiments and these kind of chips environment is not so different anymore. So even if it sounds like a completely different implementation, there are a lot of similarities. And often light is used to communicate between those ions. This is an overview. It's not complete but in the last 5 years there have been enormous changes there's a lot of companies who invest in superconducting qubits, but essentially it doesn't matter if you have real ions or artificial ions, or at the end, or even a photon is just a 2-level quantum system that has unitary dynamics, and measurements are performed on it. So essentially, all these quantum computers are individual quantum systems, and we use the laws of quantum physics to implement computations. So the physics behind these kind of devices is essentially basic light-matter interactions at the level of single particles. So let's go back to the initial experiments. How can we create, for example, an entangled state for quantum computing? And one way of doing that, so initially when the idea of quantum, so initially ion traps experiments, they were in the 1990s, they were developed to perform tests of our fundamental understanding of quantum physics. Nobody thought about applications, maybe apart from the clocks. But mainly they were there to really test foundations on our understanding of light-matter interactions. But then it was realized that they can be used for quantum computing. And then when this idea started to take off, then some people thought, okay, but because you have photon emission, and because you always have a quantum system, you have a small error, and then that error will propagate because of the unitary dynamics of these systems. Yeah. So if your unitary dynamics changes, rotates your state vector a little bit, but rotates a bit further than you want to, then that error, if you do many of these little errors, they will just add up, and any exponential speed up you might get for your quantum computation will just get destroyed immediately by those kind of errors. And what I want to show you is that this is not the case, because we have nonlinear dynamics of the atoms. You have measurements and quantum jumps, and you can use those measurements, you can use dissipation to stabilize your dynamics of your system. The only thing you have to make sure is that your system is designed in a way that you never learn the information that is in your qubits. Then it stays in there, and you can guide your system, do error correction, and correct for errors as you can in a classical computer, and that's not a problem. That's why having an open quantum system and understanding spontaneous photon emission and the measurement process and how to implement it is quite important for making these devices work on the scale that our people are looking at now. For example, let's look at this is a very simple scheme to prepare two atoms or ions in an entangled state. So you put them in an optical cavity that traps light, and the important thing is that the cavity will emit photons in here. So you seeing a photon coming out here will not tell you what the state of the atom is, or which atom created the photon. And we drive the atoms from the side. So in this way, we pump energy into the atoms, so we couple, let's say an atom is in a ground state, we couple it to another ground state, but then the one laser also can be used to then put photons into the cavity whenever the atom is here. And now we have two atoms sitting here. So in general, they will just emit light. But the nice thing that happens here is when they are in a symmetric state, they will couple very strongly to the cavity field, and they will produce large photons coming out of here. But sometimes, via spontaneous photon emission from this excited state, the atoms might end up in an antisymmetric state, and this is the dark state of the system. So it's a state 0, 1, minus 1, 0, where they don't see, because of their symmetry being antisymmetric, they don't see the coupling to the cavity anymore. And then you can pump in laser, you can pump in energy as much as you like, there won't be any light coming out. So that means whenever your intensity of the light that's coming out here stops, you know that your atoms have randomly entered the macroscopic dark period, and they are now in a maximally entangled state. So just observing these light and dark periods tells you, it doesn't matter if your laser fluctuates or if there are some, as long as the symmetry of your system is preserved, you know that if this detector goes dark, your atom are in an entangled state, and it will stay in that entangled state if you turn your lasers off at that time. So you have a very robust scheme for the generation of entangled states, atomic states. Here are more details of how the scheme works. Yeah, so it's the spontaneous emission from excited levels, which is very small because this laser is highly detuned. So you can use quantum jumps. So this will be the dark state of the system. And if you then turn your lasers off, the system stays there. So this is a simulation of the macroscopic light and dark periods that you would get. And even if your system is has quite large decay rates, I won't go into the details because of time. I don't want to run over. But the idea is that even if you have relatively high spontaneous decay rates in your system, via this measurement process, you can create entangled states with very high probabilities. And then once you have two atoms entangled, then you can take this state and do some kind of projection measurement. without learning exactly, so you measure whether the atoms are in 0, 1 or 1, 0, without measuring which one it is. And in that way, you can take 2 pairs of entangled atoms and make it a pair of 4 entangled atoms without losing, without reducing the number of atoms in the process. So you can fuse smaller entangled pairs together to bigger entangled pairs. And if you can move the atoms in and out of cavities, so you can entangle 2 atoms, move this one out, move the next one in, fuse them together and build large entangled states, and then they would be the resource for a quantum computation. So you can grow large cluster states and to detect if you are in a, for example, if you have maximum interference, then maximum emission, you know you're in a state that where both atoms are initially in the one state, and you can see that immediately from having photon emission at a relatively high rate. If you have a medium rate, the photons come out of your cavity slowly, then you know they are either in 0, 1 and 1, 0, but you never learn which one, and then that implements a successful parity measurement, or you get the right outcome that you need to fuse pairs together. So these schemes of fusing entangled pairs into larger entangled states is a probabilistic process. What people like Terry Rudolph realized, or Peter Koch, or other people at the time, Terry Rudolph is the one who is one of the CEOs of PsiQuantum, is that even if you can only do operations probabilistically, you can create resources, create large resources, which then give you a speed up when you perform a quantum computation. Yeah, so macroscopic quantum jumps and measurements of photonic states, they are a nice tool that on your single quantum system to control it and to avoid errors and to avoid the propagation of errors. Another important application, I'm aware of the time that I have only 10 minutes left. Another application so I want to show you also an application for the double slit experiment, how you can use the interference in the double experiment to distributed quantum computing. So entangling atoms locally is not enough. At the end, you also need one computer to talk to another computer, or to have different parts of the computer talking to each other. A big enhancement also comes from, instead of talking only to next neighbors, if you can have more connectivity and you can have, let's say, a string of ions, but you can have this ion talking immediately to this ion without having to propagate information through all the ions that are sitting in the middle. Yeah, and in order to do that, you would use photon emission and the interference that we've seen in the double slit experiment. So, so if you put an atom in a cavity, but it could also be a quantum dot, it could be any kind of system that can release light in the optical regime. Then, so the cavity, these are two mirrors surrounding the atom. They make sure that the photon goes in not randomly anywhere in space, but where you want it to go. And by putting a laser pulse, you can generate a single photon on demand with a process that is called the Thrissur process. So it's not allowed. So the laws of quantum physics, they forbid us to clone a quantum system. So if I have a quantum state, I cannot make a copy of it without destroying it. But one thing that is not forbidden is to do some double encoding. So I have a quantum system in a state G, and then to produce a state G and 1. Yeah. So if I'm in G, if your atom is initially here, you create exactly one photon. So that this you can do, and that, for example, what you can do is if you have a superposition, yeah, like this would be a qubit state. You have two atomic states that encode your information. Then what you can do is a double encoding. So, for example, if your atom is in 0, you create a photon at an early time. If your your atom is initially in 1, then you create a photon at a short time later, and in this way you have the information that was initially only in the atom. You now have that information in the atom and the photon field, and then you can send this photon. You can use this photon to communicate, to have one atom on one side communicating with an atom that's further away. And what we showed at the time is that you can do deterministic gate operations. So as long as you make sure that when you measure the photons, you never measure in a state that tells you what the state of your atom is. So for example, you can measure early plus late or early minus late, then you will never learn what alpha and beta are. So you measure in a so-called mutually unbiased basis. Then even if you don't get the measurement outcome that you want, because you still have your information in your atom, you can repeat your computation or your gate operation until it works. So, and we call this repeat until success quantum computing. So your initial qubit state, your initial state of the two atoms might be something like that. So this is a general 2-qubit state. You do your double encoding for both atoms. So then if your atom was in 0, 0, you might be in create 2 early photons, or you might have an early and a late photon. Then if you measure in a way, so use the linear optic setup in a way that when you detect 2 photons, but you never learn whether they were early or late. Yeah, so you have to mix them in a way and superpose them in a way that you don't learn if it was early or not. Then your final state of the atoms after your detection looks like this, and that is a way of, even if your atoms were initially not entangled, if you measure an entangled state, you can entangle them. And what we found is that these measurements of states like this can be performed, and you can measure, even if you can't measure a complete set of basis states where all of them are entangled, because you never lose your information, you can design a repeat until success quantum computing gate. Yeah, so you can have maybe if you measure a certain 2-qubit output states, then you know entangled your atoms, or you implemented a gate operation. Or if you measure a state that does not change your atom, has not changed your atom, then you just do it again until you succeed with the gate that you want to implement. So you can process information, in short, you can process information between 2 atoms that are far away using interference effects by just doing measurements on the photons, and you can do it deterministically. So you have 2 sources, they create these double encoded photons. You send them to a linear optics network that removes the information of whether your photons were early or late, so delays the early ones and so on, and then you detect them, and when you detect 2 photons, you have changed the information in the atoms, even if you don't know what that was and they are far away. And then if you have many sources, if you have many ions, you can entangle large strings of ions, and then later on, if you want to do a computation, you can use this as a resource. Okay, maybe I rushed this last bit a little bit, but the important thing is that even if these kind of experimental setup that form these quantum computers look quite sophisticated, essentially the basic physics that they are playing with and that they are using in order to make those gates, those implementations robust against errors and to build as large entangled states as possible that you might need for really useful quantum computation, then the physics is still very much the physics that we learned in the 1990s. Yeah. So that there are, of course, many more applications. I think what's exciting at the moment is that, initially people were aiming for building a quantum computer, or we're still aiming for a quantum computer, but there are many other applications where you don't need as high a precision as for a quantum computer, like applications in quantum metrology and quantum sensing. And a lot of systems in photonics, they behaving more and more like those huge trapped ions that did quantum optics experiments in the beginning. So quantum photonics is an area, or photonics is an area where the effects of single quantum systems they can be realized in there as well, and this probably creates a lot of opportunities for developing completely new technologies. That was all from me.